Last thing in this chapter that we're covering is ideal gas model and introducing that. To begin that, we need to start with the universal gas constant. And so this is the universal gas constant. It's R with the bar over it. And all three of these are used. It depends on what other things you have. But these are the universal gas constant. We have this compressibility factor, Z, and Z equals pressure times V bar, which is, when we put the bar over things, we're talking on a per mole basis. So that is specific volume on a per mole basis. R is the universal gas constant on a per mole basis, and T is temperature. This would also equal the Z factor can also equal pressure times specific volume times the in universal gas constant for specific substance times temperature. So our the specific volume on a per mole basis is equal to the molecular weight times the specific volume, and the our universal gas constant is the R multiplied by M as well, when the M is the atomic or molecular weight, and you can find those on table A1. Also, they list here on table A3 in your chapter 3 values of the gas constant R for selected elements and compounds. So they include the molecular weight in there. We have the generalized compressibility chart, the Z chart. PR is the reduced pressure and TR is the reduced temperature. Both are dimensionless and given by PR equals our pressure over the PC, and T equals TR over TC, TR equals T over TC. And we can use that to look at this general compressibility chart for various gases. And that brings us to the ideal gas model. So introducing the ideal gas model for states when pressure P is small relative to critical pressure, PC. So this gives us a low, if we have a low reduced pressure. So if this is low, a small number, then we can use the ideal gas model. Or if temperature is large relative, so if P is small relative to critical pressure, or T is large relative to critical pressure, so if this is a low number and this is a high number, small or big number, then our Z is approximately equal to 1. So the compressibility factor here, this is approximately equal to 1. When that happens, looking on the chart. Anyway, then we can use the ideal gas model. So if Z is approximately equal to 1, then the ideal gas equation is given by PV equals RT. And we have these other forms, they're all the same, like just different basis. So this is pressure times specific volume times universal gas constant times temperature, and so on. We have pressure times volume, and that one includes mass on the other side, and so on a per mole basis, and so on. So for an ideal gas model for any gas whose equations are given exactly by PV equals RT, so this means we have a Z of 1. Specific internal energy depends on temperature only, and specific enthalpy is also depends on temperature only. So subbing U is a function of T, and PV equals RT, then enthalpy equals the internal energy at a specific at a temperature, specific internal energy at a given temperature, plus the universal gas constant times the temperature. Internal energy and enthalpy usually have two independent properties. if we have the ideal gas, then we only need temperature to find the internal energy and the enthalpy. So key aspects of the ideal gas model, PV equals RT, meaning that Z equals 1. U is a function of temperature only, not two variables, but just one. And then enthalpy is equal to the enthalpy at a specific, at some given temperature, at a certain temperature, equals the internal energy at the temperature plus the universal gas constant for that substance multiplied by temperature. And if you recall, the specific heats were partial derivatives. But if for ideal gas, because we're only dependent on a single variable temperature, they're no longer partial derivatives. We can use ordinary differential instead. If we have that and we separate our variables, we get du equal to dV. The specific heat is a function of temperature, dt, and the so this is first one's internal energy, and the second one is enthalpy. And if we integrate them from T1 to T2, we get a change in specific internal energy and a change in enthalpy given by, so this is the internal energy equals this for an ideal gas, and the specific change in specific enthalpy, so internal energy, enthalpy, and then we have for an ideal gas, we have these specific heats, and then our specific heat ratio. And we can use those to help us solve problems. And lastly, we have polytropic process relations. And so a polytropic process is a quasi-equilibrium process described by PV to the nth power equals a constant, or P small v to the n power equals a constant, where n is also a constant. We saw this in chapter 2 as well. So that just defines a polytropic process relationship. But for an ideal gas, then, and you can see section 315 for the development of this, but this is equation 356. So the temperature at the second, so we are going from 1 to 2, the temperature at the second divided by the temperature at the first equals the ratio of the pressure at the second divided by the pressure at the first, raised to the power of n minus 1 over n, and that equals the volume at 1 divided by the volume at 2 raised to a power of n minus 1. And we can use this to help us solve problems. It is definitely a monster of a chapter. I hope you hung in there and just keep at this, because we will use these things throughout the rest of this semester and throughout the rest of your time with thermodynamics. So it's a super important chapter, and getting all these concepts down is really important. Good luck to you.